So we're continuing with the nervous system. In this case, we're continuing with the senses. And we're going to get to hearing. I'm sorry if the sound on these things is not super, is that it is a limitation on the iPad that I'm using. I need to get a microphone or stand closer to the iPad, which is what I'm going to do right this second. So what you're registering with your sound of hearing is vibrations from the environment, which for our distant ancestors that lived in the water, didn't necessarily need a specialized hearing organ because water carries sound much more powerfully. The vibrations are stronger, and a particular type of touch could pick up sounds going through the water. That's why you don't find ears in fish. And a lot of animals that live in the water don't have specialized hearing structures. On land, the air doesn't carry the vibrations terribly well. And so you find a lot of specialized hearing structures in land animals. And ours, we've got a sound gatherer, what's called the pinna, the outer part of your ear. And the way that it funnels sound down into the canal makes the sound slightly different depending on where it's coming, high to low. I'll fix that in a second. And our ability to localize sounds is not super. Is that other animals do it fairly well because they have bigger ears that they can steer. Now, there's a sound over there. You can see their ears turn, or they turn their heads, and they have these big sound gatherers. We're not that great. Directionality is that the difference in time between sound reaching this side and that side is so quick that physics people have said, well, you can't be reading the difference in arrival in order to tell the direction. To which the biologists go, so how are we doing it then? And they go, well, you can't do it that way. And we're probably going to turn out to have some sort of special processor that allows us to read the very tiny difference in sound arrival between sounds coming this way and hitting this side and sounds going around and hitting this side with the same sound. But right now there's some argument about it. You have this canal. You'll notice I'm giving you a chance to write stuff down, but I'm not doing a lot of writing on this one because I want to use these as much as I can. So I'm expecting you to kind of write as I go along. You've been adding stuff to my little bitty notes as you went along anyway, so we're just kind of expanding that. At this point in the semester, you should be kind of ready for that. So here's the canal. It is lined with cells that produce a waxy substance. Why? That's another thing. It probably has something to do with conducting sound, but the thing about wax in the ear canal is that it's pretty easy to get it out of there, to treat it with a very gentle chemical and dissolve it away. And then test all the various things. You know, can you hear sound better? Can you not hear sound better? Does it affect the directionality perception? Does it, are bugs more able to crawl into? There's all sorts of theories about it. And nothing really seems to hold up to testing. And it may be that whatever this does, it was very effective for one of our ancestors, but it doesn't really do much in particular for us. Kind of like goosebumps. But nobody knows for sure. So the sound comes in. Here's your tympanum, your eardrum. It goes completely across the canal. I mentioned this before. Here's the eustachian tube that allows you to equalize pressure on this side against that side. If you go up and the pressure drops, this would be air pressure from the lower, and it would push the eardrum out. And when you push the drum head out, it vibrates differently. If you're coming down, the opposite happens. The pressure out here goes up. This is the pressure from up top, and it would push the eardrum in. This allows air from the nasal passage in and out of this chamber to get this pressure and that pressure equal. Now the eardrum vibrates, And this bone vibrates, and that bone vibrates, and that bone vibrates. This is the middle ear. And it isn't directly connected to your sound receptors. And in some animals, there's a single bone to transmit this. In fact, that's one of the major differences between reptiles and mammals, is that we have 3 bones here, and reptiles only have 1. They have the other 2 bones. They're actually on the top of the jaw. And when you're looking at distant fossils, there was a period of time where looking at the basic shape doesn't really tell you whether you're looking at a mammal or a reptile. There were some very lizardy-looking mammally relatives and some very doggy-looking reptile relatives. And one of the things they hoped to find is skulls with the bones. So that if there's 3 bones in here, it's a mammal. If there's 1 bone in here, it's a reptile. If there's 2 bones in there, which they've discovered in a fossil not very long ago, maybe it's a transitional form. Yeah. So these bones vibrate when this vibrates. Right there is a little bitty muscle. And if a very loud sound goes off, and one of the first things that happens is that muscle tenses up. So very loud sound on your eardrum, very loud sound on these bones, going back to potentially damaging the inner ear where the readers are, the receptors are, and the muscle goes, and the bone can't vibrate, so the sound gets cut off. That's why after a very loud sound goes off, you can't hear anything for a while. It takes a while for the muscle to relax. Now the sound, that initial sound is going to get through. I'm going to talk about that in a second. But it keeps, because when you have a loud sound go off, you don't know that it's going to be brief or long term. So the system is set up to protect you from a long-term sound. I mean, it's not psychic. It doesn't know the sound's about to come. So here's your middle ear with that air-filled space. Here's your hammer, anvil, and stirrup. The stirrup touches on a little membrane window, there it is, into this weird looking thing. This is your cochlea or cochlea. That's a word related to snails. It looks like a snail shell. And there's a long chamber in there. It gets smaller and smaller and smaller. That's what the coiled snail shell looks like. And there's a couple of membranes. There's a space inside, a couple of membranes going across. There's a supporting membrane for this thing, and then a basement membrane for this thing. And here's what's happening. There's a structure hanging over this, and there's little bitty hair cell connectors. In the wide part of the tube, the hair cells are fairly thick and they register low sounds. As it gets smaller and smaller, the hair cells get finer and finer, and they register upper pitch sounds. Now, not too surprisingly, the thin ones that register upper pitch sounds are more fragile. Exposure to loud sounds can damage them over your lifetime. I've experienced that where when I was in, well, actually a few different places, worked in factories. At one point worked in the Sealy mattress factory doing quilting surfaces for the mattresses, and in which case you're actually working inside the machines a lot, loud machines. I never did find an ear protection that didn't fill my ears up with wax. So I just have dealt with the damage that, and I tell people this in the lab, I don't hear that well. But what I don't hear is upper range. So I'm gonna have much more trouble figuring out what a woman is saying with an upper pitch voice than a male is saying with a lower pitch voice, because it's those upper ranges that you lose. All those people that drive past me and half a mile away, I can hear your car stereo. It's, I'd rather have my hearing at this age. So this goes round and round and round and round and round. Can you see that up there? And at the terminal end, there is the cellular equivalent of a big pillow. It's a shock absorber. So the sound goes in, it goes round and around and around, and boom, it hits the sound absorber, and that absorbs it at the end. Remember I said I'd come back to this. A really loud sound, it overwhelms the little pillow at the end. And so it goes round and round and round, boom, bounces back, round and round and round and round. Hits the membrane window, round and round and round and round. And that's where a loud sound causes ringing in your ears. Because the pillow is absorbing some sound, and what's coming out isn't exactly the sound that you heard, but it's sound. And so it just kind of persists for a while until it kind of dies down. Now, of course, there's issues with the system where messages, stray messages, or messages not even from inside this chamber, but from the connectors along the way. The connectors along the way, where you always are hearing what you think is a sound, but it's actually being generated inside the system somewhere. It's tinnitus or tinnitus, a persistent ringing in the ears, and that can be really difficult to figure out what's going on. Right here and in here. Sight, hearing, taste, smell, touch, 5 senses, right? Nah, way more than 5 senses. One sense which definitely should be on the list, not the 6th sense of some sort of psychic stuff, but a sense that it reads a totally different aspect of the environment, is balance. And because your balance sense is in your inner ear, and it goes into your brain through the same nerve, it's been lumped in with hearing, like it was hearing. It isn't. It isn't hearing in any way, shape, or form, except that you do read some form of vibrations, but that's weird. It's not air vibrations. You have 2 basic balance senses. You have what's called static balance. Static balance allows you to read down, direction of gravity. And there's 2 very low-tech ways to do that. You have 2 chambers, one in each ear. And in each chamber, there is, hanging from the top of the chamber, a little bell. And sticking up from the bottom of the chamber, if my hand was a lot smaller, and I don't really have anything to substitute here, is a little Tootsie Pop. Now, the bell hangs down according to gravity, so that if you tilt your head, it swings over, right? It swings depending on how gravity is working. But the little knob, when you tilt your head, it moves with your head. And what it'll do is it will touch the edge of the bell. Tilt your head. And there's detectors along the edge of the bell that tell you, we're tilting our head. That's one detector. The other detector is even weirder. You have 2 chambers, and on the bottom of the chambers are these things that look like old-fashioned AstroTurf, like plastic filaments. They're not plastic, but that's what AstroTurf is. All these filaments, modified cilia, sticking up, and into that chamber you secrete, honest to goodness, little rocks, nitrogen-based rocks, and they sit on the filaments. And as long as you're standing up straight, the filaments support them. But if you tilt your head, they push down on the edges, and the filaments start to touch one another. And there's detectors that tell you that, so it tells you that your head is tilted. That is static balance. Then there's moving balance. You can really see the detectors here. What are called your semicircular canals. And you have semicircular canals oriented this way. They read movement this way. You have them oriented that way. They read movement this way. And you have them oriented this way. They read movement that way. How do they do that? There's fluid in the canal. And when you move this way, the canal moves and the fluid lags behind a little bit. Like grabbing a bucket of water or a dish pan and trying to move it too fast. The water tries to stay where it was, sloshes out. Here, you move the canals, the liquid lags behind, and it pushes backwards on detectors. This way, same thing. This way, same thing. And your body reads that as motion. You're moving, it's an inertial reader as opposed to a gravity reader. And those are your two balance senses located in your ear. Okay, where am I here? Smell and taste both read chemicals. Taste is pretty much contact, right? You gotta touch your tongue, gotta dissolve into the liquid on your tongue, and you have very basic detectors. How many different detectors you have is a matter for debate. Classic ones are salty, sweet, bitter, and crap, what's the last one? Salty, sweet, bitter. Terrible to get old. It'll come to me. But savory is supposed to be one. There's a specialized one only some people have. I think we're up to 8 or 9 suggested different types of contact detectors, but they're not very sensitive. Like your sweet detectors will pick up a whole bunch of different types of molecules, which is why we use artificial sweeteners. Artificial sweeteners are something like aspartame, NutraSweet. It's not even a sugar. It's actually 2 amino acids that happen to fit into the detector, and so your detector goes, yeah, that's sweet. Salty picks up positive ions. I wouldn't have thought I'd have needed to write that down, but I guess I need to write that down. They work with the chemical detectors in your nose. We talked about that when we talked about breathing and how you have that olfactory epithelium. Your nasal receptors are very complex. And the latest research suggests that as we go through life and are exposed to new smells, we will actually build specific receptors for specific types of smells that we keep running into. Almost the same way we build antibody molecules, where the molecule in the smell, right, it's the molecules touching the top surface of your nasal epithelium. They touch, and then we have a receptor, first generalized smell receptors, and then more specific smell receptors as we go through life. And the ability of people to build more and more specific receptors may have to do with, senses of precise smell. Our sense of smell is not great compared to other animals, but it's not terrible either. And of course, your sense of taste really doesn't work without your sense of smell involved. Air goes up the back passage to your nasal passage also, so when you're eating, you get a sense of smell, and of course this thing is aimed at where we're putting food in our mouth. So you put those two senses together. If your head's really stopped up, if the back part of the passage stops up, it affects your taste. If the front part and the back part is stopped up, your taste is really compromised. Coronavirus, one of the more common symptoms is you lose your sense of taste and smell. I haven't seen anything to suggest exactly how that happens, but it happens. And in some people, it doesn't come back normal. Okay, sense of touch. Remember I said there's more than 5 senses and talked about balance? There's a heck of a lot more than 5 senses that work differently. Your sense of touch actually works a couple of different ways also. There's contact. You can't really see that on the picture, but the cells that are contact receptors are built almost like a dried up onion with a bunch of layers that don't quite touch one another unless you push on them. And then the membranes touch each other, it sends a message to your brain. You push on a bunch of them, you get more of a contact sensation. If you push on a whole bunch of them or you really compress them, you may get a response that registers as pain. But you do have pain receptors that are chemical receptors, like your smell and taste. And they pick up chemicals from inside living cells that should only be around the receptors if those cells have been broken open, damaged. So you have pain receptors that specifically read local damage and send a message to your brain. I mean, your pain sensation is basically a way of saying to your brain, figure out what's going on and stop doing it. We're in trouble down here, we're getting damaged. And so your brain goes, okay, I'll move away from the fire, or, there's nothing I can do about this right now. In fact, your pain sensations are tamped down by adrenaline, fight or flight. We also read temperature flow through the skin. Not temperature in and of itself, but heat flow. If heat's going out, it registers as cool. If heat's coming in, it registers as warm. I used to do this test in the lab. You can do this at home. It's kind of a fun test, especially when I tell you the weird part of it. I don't do it anymore because keeping the thing going and stabilized in a lab with a bunch of people moving around is tough to do. But used to be, set up 3 containers, 2 decent sized ones and a big one. Ice water, hot water, lukewarm water. Put your hands into the ice water and the hot water. Probably better if it was just cold, but to keep it going in the lab, I tended to use ice. Let them get in there for a little bit, let them get used to it, and then put them both into the lukewarm water together. Well, the one coming from cold is gonna feel warm, the one coming from warm is gonna feel cool. They're in the same water, but they don't feel it the same. That's interesting. One of my students many years ago went, and I went, what? She said, I touched my fingers to each other and the sensation went away. And that's what happens. Your brain gets very confused. If you have them both in the lukewarm water and you touch them, now your brain's got to deal with the fact that they feel like they're in different environments, but they're in contact with each other. And how your brain responds to that is different in different people. Most people, the heat-cold sensation in the fingers will disappear. In some people, it'll be more of the hands. In some people, the 2 different temperature sensations go away entirely. As long as they're in contact, they don't feel hot or cold. And the interesting thing then is, if you separate them out again, the sensations come back. It's like your brain goes, okay, now they're in totally different environments, now that they're not touching each other. So it's an interesting test around. The last touch sensation is called proprioception. I think about this all the time because I'm a weird biologist, and it happens a lot. Early on, we had the masks that you tie in the back. Well, you can't do that unless you know where everything is that's working to do the tying. And that's what proprioception is. You have detectors all over your body, embedded well inside the surfaces, that tells your body, here's where my hand is. And I can adjust my belt in the back because I know where my hand is, and I know more or less where my belt is. Once I feel it, I know what's going on. I get in my car, I put my key in the ignition. I don't lean over and look to see. Well, every once in a while I do because I miss. But I'm used to it, and I know where my hand is, and if I'm seated right, I know from experience where that point in space is for the key to go into. And that's proprioception, your ability to use your appendages without having to look at them all the time. Okay, that's it for the senses. Now we'll get back to the central nervous system, specifically the brain.